Right, welcome back, statistics scholars. Our next topic, and our first topic after the first exam, is z-scores. And this lecture, as well as our next one on probability, I want you to sort of think of them as basic tools that we're going to need to eventually ask and answer those cool research questions. Sort of the tools under our tool belt already are central tendency, the average, and variability, the standard deviation and variance that we did right before the first exam. Z-scores and the concepts we're going to talk about today are other basic tools we have to learn about as another tool in our toolbox to eventually calculate those inferential statistics, z-tests, t-tests, f-tests, etc., to ask and answer cool research questions. So, z-scores, what are they? Well, first I want to cast your mind back to our discussion of the standard deviation, where we did a data transformation, where we took a set of raw scores and then we transformed them out of their original metric and put them into different units. For example, if I've measured a person's height in inches, I might transform their height in inches to their height in centimeters. And if I have a set of people, all who have heights in inches, and I turn everybody's heights into their height in centimeters, I will have done what's called a data transformation. And we do this for a variety of reasons in statistical analysis. And what it is doing the exact same mathematical operation, to every single number in your data set. That is a data transformation, turning things from raw units into some sort of transformed metric. For example, let's say if I took, let's say I had everyone's scores on a test from 0 to 200. It was a 200-point test. I decided to take away 36 points from everybody's score because I was feeling particularly uncharitable one day. And so I took everyone's test score and I subtracted 36. That would be an example of a data transformation. And we already did a data transformation. We actually did two of them when we calculated the standard deviation. Remember that when we calculated the standard deviation, the first thing we did was subtract the average from everybody's score. Well, then we got a set of deviation scores, and that was a data transformation. Then we took everybody's deviation score and we squared it. Well, that was a second data transformation. That's the basic idea. So, how does this relate to our topic today? Well, the first thing I want you to understand is, well, I guess the next thing after data transformations is that data transformations actually come in two varieties. They come in what are called linear transformations and nonlinear transformations. And in a linear transformation, that's where you take a set of data and you add something to everybody's score, like adding 2, or you subtract something from everybody's score, like I'm going to subtract 36, or you take everyone's score and you multiply it. Let's say I multiply everyone's score by 2, or you take everyone's score and you divide. Take everyone's score and you divide by 2. By constant values. So that's an important concept. Where I take everyone's score and I subtract 2, that means I actually have to take everyone's score and subtract 2 from everybody, not 2 from some people and 3 from other people and 4 from yet other people, a constant mathematical value. And if I'm going to multiply, I take everyone's score and I have to multiply by 2, because 2 then becomes a constant. Your score times 2, my score times 2, her score by 2, his score by 2, and on and on. That is a linear transformation. If you do any other mathematical procedure, like let's say, then it's called a nonlinear transformation. And so if we think back to the standard deviation, the first thing we did was subtract everyone's score. We took everyone's score and we subtracted the average. That was a linear transformation because the average was whatever it was. It was a constant value, right? So let's say the average was 5. I would have taken everyone's score and subtracted 5. Person 1, person 2. All the people, oh, not 6, whoops. All the people, and I subtract by 5. Because that's the average. I'm subtracting the average of 5 from everybody's score. So the first step of calculating the standard deviation is in fact a linear transformation to subtract the average from everyone's score, where the average is some constant number that doesn't change from person to person, right? There's 5 people, and I calculate the average for those 5 people, the average is going to be the same for everybody. If you do any other mathematical procedure to a set of data, that is called a nonlinear transformation. And the second step in our standard deviation was an example of a nonlinear transformation. Because yes, the first thing you had to do was subtract the average, but then the second step was to square everyone's deviation scores. So the second step in a standard deviation is a nonlinear transformation. And anything else besides adding, subtracting, multiplying, or dividing is a nonlinear transformation. So let's take a look at some examples. So these are all examples of linear transformations where you take a set of data, x, we have a bunch of x scores, and we're going to add or subtract or multiply or divide. So let's say I have a set of data here, 1, 2, and let's say 5. So n is 3 because I have, let's write that down here. N is 3 because I have 3 people, right? Let's say this is the number of pets people own. 1 pet, 2 pet, 5 pets, right? I have my set of data. These are my x's. These are my x scores, right? And so I'm going to if I can do a linear transformation and it will still be linear if I add, like adding 1, or if I add the average, or the example I have here in the lecture slides, pi, right? Pi is just a symbol for a number, 3.1416, right? So adding pi would be 1 plus 3.1416. And if I do that to everybody, that is a linear transformation, just as if I would add the average to everyone's score, that would be a linear transformation. Or if I subtracted the average from everyone's score, that would be a linear transformation. Or if I multiplied the average by everyone's score, that would be a linear transformation. Or if I took everyone's score and I divided by the average, that would be a linear transformation. And why are these mathematical procedures considered linear? You might be asking yourself. And the answer to the question is because these are the mathematical procedures in the mathematical function for a straight line. Now, some of you in a previous math class may have seen this equation. Y equals mx plus b, right? This is the function for a line where m is the slope and b is the y-intercept. Oof, having to brush off some old knowledge I'm betting. Right? And so m is a number. It's called the slope. It's the rise over the run in any line equation. And b is a number. Right? And so if I had, so let me give you an example of an actual practical line equation, right? Let's say the slope is 2, and let's say the y-intercept is 3, right? I could now put in any number I wanted for x, and it would spit out a y that would end up on a perfectly straight line. So let's do that, right? I had y equals 2x plus 3. And now I have an xy coordinate plane where this is x and this is y. Hopefully this is ringing a bell. And so then I put in a number for x. Let's put in 1. So I put in 1 here, and I end up with y equals 2 times 1 plus 3. Well, 2 times 1 is 2, plus 3 is 5. So I end up with x is equal to 1 and y is equal to 5, right? So I find 1 on here, and 1, 2, 3, 4, 5 on here, and then I've got my point. Well, let's put in 2 for x. Y equals 2x. Y equals x times 2 plus 3. And now I end up with 2 times 2 is 4, plus 3 is 7. So I end up with 2 and 7. So I find 2 on here, and then I go 1, 2, 3, 4, 5, 6, 7, and this point is here. And there's my straight line. And no matter what number I put in for x, I will always, forever and ever and ever and ever and ever, always find a point on this straight line. Because let's do 3. And so I'm putting in 3 for x. Well, so now instead of 2 here, I'm putting in a 3. So let's do that. So now I'm, whoops. So now I'm putting a 3 here. And so now 2 times 3 is 6, plus 3 is 9. So I find 3 here, and then I go 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, and look at that! My point is on the line. And forever and ever and ever and ever, no matter what number I put in for x, I'm going to find myself on this straight line. And notice, in the equation, y equals mx plus b, well, here are those x's again, right? X's. Notice how I'm multiplying here and I'm adding here. And so these are the mathematical equations that, when you think about a function, always end up with a straight line, where no matter where you look on that shape, the pattern never changes. And so that's why we call it a linear transformation. When we add or subtract, because adding and subtracting are the same mathematical function, right? This would still be the equation for a straight line, even if I have a negative y-intercept, and adding and subtracting is linear, right? In addition, I can have, but here we're multiplying, right? And so multiplication is a part of a linear transformation, as is division. Because I can have a slope that's like a fraction, which is sort of like taking x and dividing by 2. Right? And that would still be the equation for a straight line. So taking a bunch of x's, adding or subtracting a number from them, or multiplying or dividing is always, always a linear transformation. And why does this matter? Well, this matters because, remember, we're talking about data, a set of data about people. And remember that we can look at pictures of our data. We can look at the distributions of our data. Are our distributions normal? Are our distributions uniform? Are our distributions skewed, right? No matter what the original shape of the data, if you take everyone's scores and you add a number to it, take everyone's scores and subtract a number, take everyone's scores and multiply a number, take everyone's scores and divide by a particular number, whatever the original shape of the distribution, normal, uniform, skewed, the relationship between all of your people is going to be completely unchanged. The only thing that will change are the numbers at the bottom, because in a linear transformation, the relationship between the people is completely unchanged. Like on a straight line, the pattern never changes. It's always just a straight line. It's always just a straight line. The relationship between all the different numbers is always just this steady up and down with no weird curves. The same thing with a linear transformation with data. How your people are related to one another doesn't change. If there was a normal distribution before, it's still normal. If it was a skewed distribution before, it's still a skewed distribution. And that's why that's important, to know the difference between a linear and a nonlinear transformation. If I take everyone's scores on the last exam and I add 3 points, the top person in the class is still the top person. And the second person in the class is still as high as they were above the third person. The relative relationship among all of your people is going to remain unchanged. It's just the number that gets assigned to them is going to be altered. But if I drew a picture, like on a density plot or a histogram, the relationship between all of your people and their scores is exactly the same, the relative relationship. Contrast that with a nonlinear transformation. Nonlinear transformations do change the shape of the data. They alter some numbers more than others. For example, powers is a nonlinear transformation because large numbers get affected more than small numbers. 1 squared is still 1. 2 squared is 4. But 5 squared is 25. The bigger the number is, the more squaring affects it. And so the shape of your distribution, the relationship between your people and their scores is going to be altered because bigger numbers are going to be more affected than smaller numbers. It's the same thing with square roots. Square roots affect larger numbers more than they do smaller numbers. So it's going to change the shape of your distribution by altering how your participants and their scores are related to one another. And it's the same thing with a log transformation. Now, we're not going to do logs in here, but you should know a log is an example of something you can do to data that is not adding, subtracting, multiplying, or dividing, and so it is a nonlinear transformation. And an inverse operation is also a nonlinear transformation. And it's a little, so I wanted to show you that one as well. So this is a nonlinear transformation as well, because instead of taking, let's say I have, now let me give you my set of scores from before, 1, 2, and 5. If I was going to divide everyone's score by 2, that would be going x divided by 2, and that would be a linear transformation, right? But if I decide to do it differently, instead of dividing everyone's score by 2, if I decide to take everyone's score and shove it into the bottom of a fraction, 1, 2, and 5, if I decide to go, oh, well, I'm going to do the inverse operation, 1 over 1, 1 over 2, 1 over 5, that's not division because I'm not taking 1, 2, and 5 and dividing by something. I'm taking all my x's and I'm putting them into the bottom of a fraction. And that is the inverse operation, if you remember that from a previous math class. And that is a nonlinear transformation. And why this matters in relation to people is because all of these different mathematical operations that you could do to every single number in a data set is a nonlinear transformation, and so is going to not keep how your people's scores are related to each other the same. Nonlinear. The shape of your distribution is going to be different. If it was skewed before, it may not be skewed anymore. If it was skewed before, it may be less skewed now. If it was normal before, well, now maybe it has skew. So a nonlinear transformation changes that shape of the distribution. So keep in mind that inverse operation is a nonlinear transformation, and don't get confused, right? 3 over x and pi over x, right? This is a nonlinear transformation, even if x over 3 is linear. Because imagine the data set, 1, 2, and 5. Taking everyone's x score, because these are the x scores, and dividing everyone's score by the same number is completely linear. But then if you go 3 over 1, 2, let's see, 3 over 2, and then 3 over 5, what you're doing is shoving your original data into the bottom part of the fraction, which is called the inverse operation and is not division. It's not. That is the inverse operation. To take 2 and turn it into 1/2. To take 3 and to turn it into 1/3. To take 5 and to turn it into 1/5. To take 100 and turn it into 1/100. That is the inverse operation, and it is not linear. So just keep that in mind. So let's make sure we understand what I meant. Which one of these is the nonlinear transformation? And I promise you there's only one of them. Take a minute and look at it and decide. Well, the right answer here, are you ready? Is this. And you're like, wait, but I see a square there. I see a square there. That's nonlinear. Ah, yes, but order of operations. What's really going on in A? A, what you're doing is squaring pi. You're going to get 3.1416, and you're going to multiply it by 3.1416. So you'll end up with something like 9.5. And then 9.5 times 3, and so you'll end up with something like 30-ish. So you're basically going to take everybody's score and add 30-ish. Again, completely linear. Order of operations. Notice that. Take pi x minus 2. That's B. That is, of course, completely linear. Subtracting 2 is linear because you're just subtracting something. Taking everyone's score x and multiplying it by pi is completely linear. X over 3, totally linear. Here are my x scores, 1, 2, and 5. Simply dividing by 3 first, totally linear. And then subtracting 3.1416. Another linear operation. But D is in fact nonlinear because I took my values 1, 2, and 5 and put them in the bottom part of the fraction and then multiplied them by 3. That inverse operation of putting x in the bottom is nonlinear. So I imagine you may have to decide in your near future. I'm going to give you a list of equations like this and ask you, if you did this to all of your x's, if you did this to all of your scores, would it be linear or nonlinear? And you're going to have to pick out the nonlinear and linear transformations. So let's actually look at some distributions. Here I have 2 distributions, and it's distributions of 200 scores. These are density plots. So again, turning real data into, let's say we have an infinite amount of data. And as you can see, it's a positively skewed distribution. And notice that the numbers at the bottom range from -2 to positive, range from -2 to +12, right? So the range is going to be 14, right? So 14 points, ranges from -2 to 12. And then I decide to linearly transform it by adding 4 to everyone's scores. And what you'll notice is this distribution that is positively skewed. The tail of the skew points in the direction of the skew. It's right hand positive skew. Notice that it shifts down the number line. The numbers at the bottom change because now whoever had a -2 before, I'm going to add 4 to their score, and now they're going to have a +2, right? Anyone who had a 4 before is now going to have an 8. Let's just look at that, right? All the people that had a score of 4 now have a score of 8. Everyone's scores have just shifted down the number line by 4 because I added 4 to everyone's values. But the person who had 4 still has 4 more than the person who had 0, because now anybody who had 0 has 4. So the relationship between your people is preserved, right? It's just everyone who used to be 4 is now 8, and everyone who used to be 0 is now 4. Linear. You've not changed how your people's scores are related to each other, and so the shape of your distribution is unchanged. It was skewed before I added 4 to everyone's score, and it's still skewed. Or how about this one? I've taken everyone's score and I've added 3. So I've moved everyone's score up the number line by 3. But then I've multiplied everyone's score by pi, 3.1416. And so anyone who used to have a 3 now has a 9 something. And everyone who used to have a 6 times 3 something is going to be Bottom line is, if I take a person's score who used to be 6, that person is here, right? That person is still going to be here on the number line no matter what, as long as I only linearly transform everyone's data. So the person who used to have 6, first I'm going to add 3 to get 9. And then I'm going to take 9 and I'm going to multiply it by pi. So 9 times 3, right? And so 9 times 3.1416 is, I believe, somewhere but like 27 or 28. And let's look over here. Where is this spot over here? Oh, look at that. This person is still over here. It's just their score is now 28 or so, 27 or 28, because I linearly transformed everyone's score. Or let's do this person, the person who used to be 2. There's a lot of people who used to have scores of 2. And first I added 3 to get 5. And then I took 5 and I multiplied it by pi to get 15-ish. And so let's find this point over here. Look at that, right? This person has just had their score transformed, but the relationship between these two people is exactly the same. The only thing that's changed are the numbers at the bottom. The shape of the distribution is the same. It's just I've shifted everyone down the number line by 3 by adding 3 to everyone's score, and then amplified the differences by a factor of 3.1416 by multiplying everyone's score by 3.1416, multiplying everyone's score by pi. The shape of the distribution is preserved. The relationship between all my 6 people and 2 people is exactly the same, but it's just now the 6 people are 28-ish and the 2 people are probably 16-ish. Does that make sense? I certainly hope so. If this is confusing, please feel free to ask in the Q&A forums. But what I think is important for you just to memorize at this point, even if it's hard to wrap your noodle around this, is when you take a set of scores, 2, let's see, 1, 2, 5, 9, 12, whatever. This is my set of X scores. This is my set of X scores, 1, 2, 5, 9, and 12. If I take all these scores and add something, take all these scores and subtract something, take all these scores and multiply. But again, it has to be the same value for everybody, right? 2, 2, plus 2, plus 2, plus 2. If it's adding, subtracting, multiplying, or dividing, that is a linear transformation. And if I graphed it with a density plot or a histogram, the shape is going to be identical for the 2 graphs. The only thing that will change is the numbers at the bottom, because people's scores are changed, they're transformed, but not how they relate to each other. The difference between my 2-person and my 6-person is exactly the same. Here's the difference between my 2-person and my 6-person. Here's the same 2 people. The only thing that's changed is their numbers, but how they relate to one another is identical. But now here is an example of a nonlinear transformation, the effect of it. And what I've done is I've taken the log function. That's a mathematical thing you can do. You can take a number and you can take the log of it. Now what log does is it actually flips skew. It basically takes any skew and it actually flips it around. It makes the skew smaller, but then also will sometimes even alter the skew. And so here on the left was my original distribution. And here was my 6-person and here was my 2-person, right? But because of and see, that's the difference between them. But here, if I find these 2 places on the distribution, things look really, really different. Here's those 6 people now, and oh my goodness, now there are a whole lot more people falling into this camp than there were before. The shape of the distribution is totally changed because the log transformation affects bigger numbers more than it affects smaller numbers. It actually takes bigger numbers and it makes them a whole lot smaller. It's the same thing with the square root. The square root affects bigger numbers more than smaller numbers. And so it changes the shape of the distribution. And let me show you this in real data. So here I have a set of numbers. Let's use the same three I have been using. 1, 2, and 5. And so let's do a linear transformation where I multiply by 2. I end up with 2, 4, and 10. And if you think about it, there was a 1-point difference between the first person and the second person. And now there's a 2-point difference. Okay. But there was a 3-point difference between the second and the third person. And now there is a 6-point difference. But the relative amplification is the same, right? 1 became 2, 2 became 4, and 5 became 10, right? There was a 1-point difference here and a 3-point difference here. Well, now there's a 2-point difference here and a 6-point difference here. We've just amplified the differences by a factor of 2, but it was the same amplification here as it was here, non-linear. But let's see what effect squaring these values has. The relative, and see how this changes things. So now I'm squaring. Wow, 1 is affected not at all. Squaring. Oh, okay. And then squaring. Oh my goodness. There was a 1-point difference and then a 3-point difference. And now there is a 3-point difference. And oh my gosh, a 21-point difference. The distance between the second and third person has been amplified way more than the difference between the first and second. And so if I graph these numbers, the shape of the original data, 1, 2, and 5, is going to be radically different compared to how the data has been transformed, because this is a nonlinear transformation. So, finally got to our topic, z-scores. Now, a z-score is a data transformation. It's a 2-step data transformation. And here's the equation for the z-score transformation, where x, see x, is everybody's score. X bar is the average. It's the sample average. So the first thing you're going to do is subtract the average from everybody's score. Hey, just like in a standard deviation, right? But then you're going to do a second step where you divide by the standard deviation. And once you've done these 2 steps to everybody's score, you have done a z-score transformation. This is also called standardization, because you're dividing by the standard deviation and because now you'll have standard scores that you can interpret. Right? This is a data transformation that is incredibly common. It's the most common data transformation, and what you're doing is turning things into what are called z-scores, or into the z metric. Instead of counting in, let's say you have the number of children, instead of counting in 1 child, 2 child, 3 children, 4 children, 5 children, you're going to do this data transformation where first you subtract the average and then you divide by the standard deviation, and now you have the z metric where you're counting in 1 z's, 2 z's, 3 z's, 4 z's, and this is called the standard metric, standardization, or the z-scores. And so, and again, x bar is just the sample average. Take everyone's score and subtract the sample average. And then as a second step, take those deviation scores. You remember that phrase? Turning everyone's scores into deviation scores, and then divide by the standard deviation. And this 2-step process transforms your data into a set of z's. And a set of z-scores tell you how many standard deviations a person is above or below the average. So if, let's say, my raw score was 36 on an exam, and I transformed my score into a z-score, and I found out that I had a z of positive 1.5. That would mean my score of 36 was 1.5 standard deviations above the average. And an additional component that is one of the reasons why standard deviations are so useful and z-scores are so useful, and the reason why you can interpret z-scores is because all z's, once you've converted everybody into z-scores, always have an average of 0 and always have a new standard deviation of 1. So let me give you an example of this. Whoops. So let's say I have a set of IQs here. I have, let's say I tell you ahead of time that the average for IQ is 100. And I tell you that the standard deviation is 15. Now, if I was going to tell you the same thing, that it was a sample, I would use X bar. And I would use S for the standard deviation. Either way. And let's say I stumble into the room and I say I've got an IQ of 90. And I'm like, okay, let's turn that into a z-score. First, I would take 90 and I'd subtract the average. And then I would divide by the standard deviation, right? So I end up with negative 10 over 15. And that would be 2/3, I believe. So negative 0.67. That is my z-score. And that would tell me that an IQ of 90 is 2/3 of one standard deviation. So 2/3 of 15, because that's the standard deviation, 2/3 of a standard deviation below the average. And I would know that if I converted everyone's IQ into z, that 100 would transform into 0 and 15 would transform into 1, because any set of z-scores has an average of 0 and a standard deviation of 1. The original variable has an average of 100 and a standard deviation of 15. But the minute I take everyone's raw scores, which had an average of 100 and a standard deviation of 15, and I take everyone's raw scores and transform them into z's, that new set of IQ scores has an average of 0, because 100 will transform itself into 0. Let's prove to ourselves that that will happen. $100 is the average. Let's turn it into a z. Minus 100 divided by 15. Well, what is 100 transformed into? That's right, 0. And so any set of z's is going to have a new average of 0, because the original average gets transformed into 0. And then once you divide everyone's score by the original standard deviation, the new standard deviation for those set of z's, not the original data, but our transformed data, is now 1. And so no matter what the variable, the minute you turn everything into a z-score, the new average is 0 and the new standard deviation is 1. And everyone's score has been transformed into a standardized, interpretable metric, because now each person's z-score tells you how many standard deviations they are above or below the average. If I go back to my example here, when I had a z-score of 0.67, I know that I'm below average because my score is negative, and I know exactly how much below average I am, 0.67 standard deviations. And that's much more interpretable than just, oh, you have a score of 90? Is that good? Is that bad? I don't know. Well, I know a z, negative 0.67, I'm below average, and I'm 2/3 of a standard deviation below average. It's more interpretable. Now, I want to point something out to you that I think is important. There's let's say now, because our use of the word standardize because z-scores are standardized. They're interpretable because you divide it by the standard deviation, and now the new set of z-scores has an average of 0 and a standard deviation of 1. Because we use this idea that z-scores are standardized, it's often really easy to then do what's called conflate, to like go, okay, well, if I turn everything into z-scores that's standardized, I'm betting the new set of z-scores is normally distributed, that bell-shaped curve. Because in our everyday life, the word standard and the word normal mean the same thing. But in statistics land, they do not. These are technical terms in statistics land. And standardization simply means you've turned things into z-scores. You've divided by the standard deviation. You've taken everybody's scores and subtracted the average, and then you divided by the standard deviation. If the average is 100, you subtracted 100. And if the standard deviation is 15, you divided by 15 from everybody's score. But normal is a word that does not mean the same thing as standardized in statistics land. A normal distribution is the shape of the distribution. Where are the people? It's not referring to any mathematical operation. It's describing the fact that most people were in the center near a peak, and that as people moved away from the center, people became less likely, the bell-shaped curve. But notice that the z-score transformation is linear. You're just subtracting the average, linear, and then dividing by the standard deviation. And that'll be a constant, right? My example from before was you took everybody's score and subtracted the average of 100, if we're talking about IQ, divide by the standard deviation. If you're doing that to everyone's score, and you need to in order for it to be a true data transformation, that is still linear because you subtract 100 from everybody's score, divide by 15 for everybody's score. That's just linear. And so if the distribution was skewed before, let's say it looks like this, the shape isn't going to change. It's still going to be skewed. And so keep that in mind, that just because you've turned things into z-scores doesn't mean that the shape of the distribution is going to change at all. In fact, it will not. Turning things into z-scores is going to keep the distribution the same shape as it was before. It's just a way to standardize the scores. So when you're looking at a big long column of numbers, the numbers are more interpretable because each number represents how much above or below average someone is in standard deviations. But it's not going to change the shape. If it was skewed before, it's skewed now. If it's uniform before, it's uniform now. Standardization and is the distribution normal are two separate concepts. A normal distribution looks pretty and bell-shaped like this, but just turning things into z-scores will not make it normal. Standardizing scores does not make them normal because standardization is turning them into z-scores, and them being normally distributed is what they would have already had to be because the z-score transformation doesn't change the shape of the distribution. So, but again, why do people get this confused? Well, because of how we use the word normal. Normal and standard in everyday conversation usually mean the same thing. Oh, he's just a standard guy. Oh, he's just a normal guy. But in statistics land, they're very, very different. Standardization refers to that mathematical operation where first we subtract the average and divide by the standard deviation. Normality refers to the shape of the distribution. And whatever the shape of the distribution was before, it's going to be the exact same now because z-scores are a linear transformation. So keep that in mind. Another reason they often get confused is because when data is already normally distributed, when it's already a pretty bell-shaped curve, turning them into z's makes a distribution that is incredibly useful called the standard normal distribution. Now it's called the standard normal distribution because A, it's normal, but it would have already had to have been normal, and now it has been standardized such that the average is 0 and the standard deviation is 1. But again, now we need to learn about the standard normal distribution because it's probably one of the single most important tools in all of statistics. So yes, this is the standard normal distribution. Now, let's put those words together. So it's standardized, which means whatever the scores were before, IQ scores, how many kids do you have, what is your height, what is your weight, whatever the X variable was, it's now been standardized, so turned into Z-scores. So it's going to have an average of 0, and whatever the standard deviation was before, now it's 1. If it was IQ, the standard deviation used to be 15, but now it's 1. If it was 2 before, it's now 1. If it was 3 before, now it's 1, right? It's going to have an average of 0 and a standard deviation of 1. Second thing, it's normally distributed. That means it's a bell-shaped curve. Now, turning things into Z-scores won't make it normal. But if it was normal already, and then you turned it standardized, now it will be the standard normal distribution. So let's go ahead and look at this picture here. Here you'll see down here at the bottom, these are the scores. Notice that the center value, the average value, is now 0 because these have been turned into Z-scores. One standard deviation away, look at that, is going to have people with the scores of 1. 2 standard deviations away, it's going to be people with the scores of 2. 3 standard deviations away, people with the scores of 3. So let's say this used to be IQ because IQ is in fact normally distributed. 0 used to be 100. The standard deviation was 15, so this would have been 115. This would have been 130. This would have been 145. But now because we've transformed it, the average is 0 and the standard deviation is 1 because they're Z-scores. And IQ was normally distributed. IQ is one of those psychological variables that has that bell-shaped curve. This could have been height, right, where the average height for women is 64 inches. But now 64 has been transformed with the Z transformation into 0. Height has a standard deviation of 2. And so this would have been 66, 64 to 66, but now it's going to be 1. Right, because all Z-scores have an average of 0 and a standard deviation of 1. And the standard normal distribution is a bell-shaped curve, a normal distribution of scores that have been standardized, turned into the Z-score metric. And so when you combine Z-scores with variables that are already normally distributed, you get this powerful tool called the standard normal distribution. Now, we want to combine one more time our knowledge of normal distributions and what they're like with our understanding of standard deviations with our new understanding of Z-scores. Now, the very last thing, one of the very last things we went over for the first exam was the area underneath the curve on a standard normal on any normal distribution. Essentially, if a variable is normally distributed, then it will be true that 68% or a proportion of 0.68 of the people's scores will be within one standard deviation. Well, because a Z-score tells us how many standard deviations someone is away from the average, and because all standard normal distributions have been standardized, that will mean 68% of all the scores, 68% of all the Z-scores will be between a Z-score of 1 and a Z-score of -1. 95%, or a proportion of 0.95, will be within the Z-scores of about 2. So 95% of the scores, 95% of the Z-scores will be between a Z-score of positive 1.96, essentially 2, and a Z-score of negative 1.96. And so this is people. 95% of the people are going to fall into this range here between a Z-score of 1.96, almost 2, and a Z-score of negative 1.96, almost negative 2. Because whatever the scores were before, now they're Z-scores with an average of 0 and a standard deviation of 1. And because 95% of all the scores will be within 2 standard deviations, well, now we're talking about Z's. And so now 95% of the cases, the scores, will be between a Z-score of 2 and -2. And 99.7, or a proportion of 0.997 of all the scores will be within a Z-score of positive 3 over here and -3 over here. And so it's the exact same thing that we learned before, right? So let's do an example. So let's say I have IQ. Let's say I have 1,000 people. So n equals 1,000. And I have a normal distribution. And IQ, and again, it's supposed to look normal. I'm not the best artist. It's not actually supposed to look skewed at all. And let's say IQ has, these 1,000 IQs have an average of 100 and a standard deviation of 15. So an average of 100. So 1 standard deviation away would be 115, and 2 standard deviations away would be 130, and 3 standard deviations away would be 145, and over here would be 85, a score of 85, 70, and 55. Now we learned before the first exam that 68% of the folks have IQs between 85 and 115. And 95% of the folks would have IQs between 70 and 130, because 85 to 115 is within 1 standard deviation, and 130 to 70 is within 2 standard deviations. Now, where do these proportions come from? Frederick Goss, integral calculus. And then we learned that 99.7 of the folks will be in here, between 145 and 55. So if there are 1,000 people, that means 680 of them, or 0.68, 680 of them will have IQs between 115 and 85, because that's within 1 standard deviation of the average of 100. There we go. So 950 people would have IQs between 950 people would have IQs between 70 and 130, because that's 95%, or 0.95 of 1,000. And 907 people will have IQ between 55 and 145, because that's 99.7, or a proportion of 0.997 of 1,000 people. All z-scores do, and all the z-score transformation does, is this. It takes all of these raw scores and it turns them into z-scores. So that anyone who used to have an IQ of 100 now has a z-score of 0. And anyone that used to have an IQ of 115 now has a z-score of 1, because they're 1 standard deviation above the average. Anyone who had an IQ of 130 now has a z-score of 2, because that's 2 standard deviations above the average. Anyone who had an IQ of 145 now has a z-score of 3, because that's 3 standard deviations above the average. Anyone who had an IQ of 85 now has a z-score of -1, because that's 1 standard deviation below the average. Anyone with an IQ of 70 now has a z-score of -2, because that's 1 standard deviation, 2 standard deviations below the average. And anyone who had an IQ of 55 has got a score of -3 because that's 3 standard deviations below the average. And now we have a new set of z-scores, which have an average of 0 and a standard deviation of 1. 100 has become 0 and 15 transformed into 1. And so this is just a standardization procedure, which makes life a whole lot easier. And then those proportions that we learned from last time, 0.68, 0.95, 0.997, still hold, except now they're applied to z-scores on a normal distribution. Now again, can you use the standard normal distribution if you have data that isn't already normal? No, you can't. Just turning something into a z-score with this equation does standardize it. You can interpret it. A person's z-score tells you how many standard deviations above or below the average a person is. So if a person has a z-score of, let's say, -1, you know that person is 1 standard deviation below average. If another person has a z-score of positive 1.5, you know that person is 1.5 standard deviations above average. And that standardization is powerful in its own right. But if you in addition, if you know that the data is normally distributed, well, now you can make the standard normal distribution that we drew right here. This is the standard normal distribution, where the average is 0, and then the standard deviation is 1. So you go up exactly 1 as you move up 1 standard deviation away. 0 to -1, -1 to -2, -2 to -3. No matter what the original units are, the average is now 0 and the standard deviation is now 1. And those proportions hold, just like we learned for any normal distribution. 68 within 1, 95 within 2, essentially 2, and 99.7 or 0.997 as a proportion within 3. Now, so here is that skewed distribution from before. And now I'm telling you that I'm going to do the standard normal. I'm not going to turn it into the standard normal distribution, but I am going to standardize it. I'm going to take everybody's score, subtract the average, and then divide by the standard deviation, because that will give me a z-score, right? That's z. That equation will give me everyone's z-score. What's going to happen to this distribution? It will be unchanged. Well, the shape of it will be unchanged. Notice that the numbers at the bottom have shifted, right? Notice that the average before is now 0, and now the standard deviation is 1. But notice also, but the shape is not changed. But notice also those 0.68, 0.95, 0.997 proportions from the normal distribution, those do not hold here, right? Because if I actually look within 1 standard deviation, that would be here and here. That's like the entire graph almost. That's not just 68%, which is why it's so important to remember that standardization simply turns things into the standard metric with averages of 0 and standard deviations of 1. If in addition you know that things are normal, then you can use those 0.68, 0.95, etc., proportions, which can be a powerful tool in statistics. But just turning things into z-scores doesn't make it normal. It will make it standardized, but not normal. And so, but z-scores are important and they're powerful, even if things aren't normal. And let me give you an example of this, why we would turn things into z-scores so we can interpret them, why standardization is important, even if we don't already know things are normal. Z-scores are useful even if the data is not normal. If the data is also normal, it's especially useful. So someone comes up to me and says, hey, this guy I know has, an awesomeness of 9.6. His name is Deadpool, and he is awesome. Sorry. That's my little joke because I love Deadpool, right? He's got an awesomeness score of 9.6. Can you believe it? And so I'm like, okay, is he awesome? I don't know. Is 9.6 good? Is it 9.6 out of 2 million? Because maybe 9.6 is not all that great. Right? But then in addition, tell you this guy has an awesomeness score. That's the raw score of 9.6. But the average for awesomeness among a group of people is 5, and it has a standard deviation of 2. Wow, that's amazing, because now I can turn this guy's score into a z-score. So let's do that. Z equals the original score, 9.6, minus the average, divided by the standard deviation. X minus x bar divided by the standard deviation. Well, 9.6 minus 5 is 4.6. 4.6 divided by 2 is 2.3. So now, what do I know about this person? I know that this person is 2.3 standard deviations above average. Not 2.3 points, but 2.3 standard deviations, right? And so that makes his score so much more interpretable, because this z-score tells me how extreme he is. It tells me in standard deviation units how many standard deviations. 2.3. Not 1 standard deviation away, not 2 standard deviations away, but 2.3 standard deviations away from the average. I now know how extreme he is. And 2.3 sounds pretty extreme to me. That suggests that he did awesome, that he is in fact much more awesome than average. Just like if let's say I said on an exam I got 36 points, and you're like, is that good? And I'm like, well, I got a z-score of 2.3. You would know I was 2.3 standard deviations. Remember, standard deviation is an index of variability. It's a standard amount. You can expect people to be different. And I'm 2.3 standard deviations higher than the average because I have a z-score of positive 2.3. That tells you how extreme I am, which is why z-scores are useful. Now, if I had a z-score of negative 2.3, you'd be like, you need to study more, because I would be 2.3 standard deviations below average, right? Because raw units are often not interpretable. In psychology and other social sciences, we measure things like awesomeness and love and aggression and anxiety. And if someone has a 20 points on an aggression scale, is 20 points a lot of aggression? I don't know. But if somebody has a z-score of positive 2.5, you're like, whoa, I'm guessing you're pretty aggressive. You're a lot more aggressive than average. You are 2.5 standard deviations more aggressive than average. That sounds like kind of a lot, right? It gives you an index of extremity. So you don't have to know how it was originally measured. You don't have to know everything about IQ or aggression or, insert psychological variable here. You can just turn things into a Z metric and talk in terms of standard deviations, which allows us to talk about things unit free of those pesky things of how did you measure it? Because now you're just talking about z-scores. How many standard deviations above or below the average is someone? So, last thing, if something is standardized, that means we've turned it into the Z metric that's going to have an average of 0 and a standard deviation of 1. If we, in addition, know how that it's normally distributed, then we can use the standard normal distribution to start talking about exactly how probable are particular people, exactly how extreme are particular scores. And that's something that I ask you to do in your second lab, where you're going to have to be getting a bunch of people's z-scores and using the standard normal distribution in the back of your book to figure out exactly how probable are certain scores or certain ranges of scores. And so let's look at this and do a couple of problems here. Let's say I tell you that on my awesomeness scale, Jenny's awesomeness scale, on Jenny's awesomeness scale, I have a z-score of 1.96. That would be, and I tell you that awesomeness is normally distributed. Now, unless I tell you that awesomeness is already normal, I can't use this pretty graph to figure things out. But let's say I tell you that that awesomeness is normally distributed. So it's got a bell-shaped curve. And I tell you that I have an awesomeness score of 1.96. That means I'm right about here, right? And we learned that 95% of all the scores, as long as it's normally distributed, 95% of the scores would be within 2 standard deviations. Technically 1.96, but within around 2. That means what's left over in the tails here? These are called the tails of the distribution. What's left over? If 95% of the pie is the blue area, what's left over in the green area? Well, 5%, or a proportion of 0.05. Because remember, proportions are out of 1 and percentages are out of 100. And so 5% is the same thing as saying a proportion of 0.05. And so that's what's left over in the little green tails is 5%, or a proportion of 0.05. And so if awesomeness is normally distributed and I have an awesome score of 1.96, how extreme am I? Well, I'm in the sort of extreme 5% of the tails, right? I'm in the extreme 5% of the folks. Only 5% of the people are as far away from 0 as I am. 2.5% of us are a whole lot more awesome, right, in the upper 2.5%, and 2.5% of the people are far away from 0, but in that non-awesome direction, non-awesome people who suck, right? And so I'm in the upper 2.5% or the extreme 5%, where you can be extremely high or extremely low. I'm in the extreme 5% with all the people that are either super awesome or super lame. And I'm in the upper, more awesome 2.5%, because half of 5 is 2.5. So you've got 2.5% or a proportion of 0.025. You got 0.025 in here. And you've also got it in here. Yeah, these are the proportions. They're out of 1. 2.5% would be 0.025. And that is how you can sort of combine our knowledge of z-scores, normality, and if variables are normally distributed, you can figure out exactly how probable is someone. Exactly how probable is somebody's score. And so let's do that with Deadpool, who had an awesomeness score of 2.3. Right? I said that Deadpool had an awesomeness score of 2.3. 2.3 z-scores, because his raw score was 9.6. And when we transformed it, it became a 2.3. And I tell you that awesomeness is normally distributed. So where is our friend Deadpool? He would be right here, right? He would be right in here. He would be in this upper tail, right? Exactly right here. This is where his score would be. And you can use the table in the back of your book. It's called the Z table to figure out exactly what proportion of people would be above him in the green tail and exactly what proportion of people would be between him and the average, right? Who would be in here. That table in the back of your book actually says, give me any Z-score you like 2.3. I'll tell you who would be above that Z-score in the tail, and I'll tell you how many people would be from this Z-score into the average. And so take a look at that table, that Z table in the back of your book, the standard normal table, and sort of familiarize yourself with it, because we'll go over it again. And that's all I have for you today, all about z-scores. And next time we'll talk about probability. And again, if you have any questions about z-scores or data transformations, do use that Q&A forum. Have a good one.